All right. It's our pleasure to introduce Alex Weeks from UBC, and he will be telling us about quiver gauge theories and symplectic singularities.
Thank you, Peter, and thank you to the organizers for the invitation to speak, and all of you for coming to listen. Unfortunately, due to the time change, I'm in Vancouver, and I've missed the morning talks, but I'm looking forward to watching them later. So it's very nice to see such interesting topics. Today, I'm going to be speaking about, yes, quivers, gauge theories, and symplectic singularities. So let me just overview what I'm going to talk about. So my plan is the overall goal is to investigate properties of what are called Coulomb branches of 3D n equals 4 quiver gauge theories. That's some terminology coming from physics, of course, but the approach that I want to follow is to use the recent mathematical construction of Braverman, Finkelberg, and Nakajima. And just to be concrete, this is all going to be about algebraic geometry over the complex numbers. There's no physics involved, actually, although it's secretly there. And so the sort of plan, though, is, well, maybe I should say, I mean, part of the reason I'm so interested in these particular Coulomb branches for quivers is because they are very closely connected to geometric representation theory. And I'll talk about that a little bit more in a moment. So the plan is roughly first to talk about some background, which is basically what is a symplectic singularity. Second is what is a Coulomb branch, at least a very sketchy overview. And then finally, discuss a proof that these varieties, which are, they're just algebraic varieties, that they have symplectic singularities. So that's the plan for my talk. So as I said, so let me just begin with some background. So what are symplectic singularities? Well, overall, I would say that there are some very interesting algebraic varieties. They have Poisson structures, and those are algebraic Poisson structures. And because I'm talking about everything over the complex numbers, when I say symplectic or Poisson or any of these words, I mean complex symplectic, complex Poisson. So these are sort of holomorphic symplectic. And these particular varieties happen to be generically symplectic. So they're Poisson, but there's just some bad parts where they're not actually symplectic. Some motivating examples, well, there's sort of the standard ones, nilpotent cone, for example, the nilpotent cone of SLN, the matrices with trivial characteristic polynomial, or in other words, just nilpotent matrices. More generally, there are nilpotent orbit closures. You have to add the word normalization because we normally demand that these should be normal varieties, and that's not always the case. And yet another example would be something like a Kleinian singularity, like a type A singularity, for example, these quotient singularities. And sort of like an overarching idea is that these varieties have some sort of interesting, I put it in like scare quotes, representation theory or enumerative properties. I won't be talking about either of those things today, but this is sort of one of the motivations for looking at these. The representation theory here is sort of a really quite a rich theory of, you look at deformation quantizations of these varieties and study modules. So this is kind of analogous to looking at an enveloping algebra instead of looking at the nilpotent cone. So there's much to say there, and I can't possibly hope to do it in 25 minutes. Oh yes, but a few more comments. One thing is that these symplectic singularities are seen to frequently arise in pairs. And now I'll start to use the physics terminology again. This comes as Coulomb and Higgs branches associated to what are called 3D n equals 4 theories. This is some sort of, the 3D n equals 4 theory is some sort of supersymmetric quantum field theory, and the Coulomb and Higgs branches are going to be some spaces associated to it. And so there's some single theory sitting in the background, and you can produce a Coulomb branch and a Higgs branch, and that is a pair. And they're often symplectic singularities. So you get this kind of duality. And mathematically, this is kind of the subject of the symplectic duality program of Braden, Licata, Proudfoot, Webster. I put an asterisk because technically they would talk about symplectic resolutions, conical symplectic resolutions. And my setting here is removing some of those words. That's a more specific notion, but we can sort of pretend that that's what they're talking about. Or we could imagine maybe what the symplectic duality program should be more general than was originally conceived. So anyway, just some buzzwords, but just as an example, so if you had a nilpotent cone of a Lie algebra and the Langlands dual Lie algebra, these are symplectic dual. So this is one of those pairs of a Coulomb branch and Higgs branch. for some theory. And since I used the word representation theory in scare quotes on the previous page, I'd just say here, representation theory means representation theory of the Lie algebras, or more precisely about what is BGG category O. So, but that's about all I'll say about that today. It's just some motivation for those of you who like representation theory. So finally, I thought I'd just briefly say, what is asymplectic singularities? What is this definition? Well, usually I'll just speak about this one. So it means a normal affine variety over the complex numbers. This is a symplectic singularity if one, we have a given symplectic form. So this is part of the data, is some symplectic form on smooth locus, an algebraic symplectic form. So just like a non-degenerate bivector, but symplectic. And second, this technical condition, which is that if you sort of try to resolve the singularities of your variety using some resolution of singularities y, then if you take the symplectic form, well, that's a priori only defined on the smooth locus. And when you pull it back, it might not be defined everywhere. But the condition is that it extends. So you pull back and it extends still to an actual two form. It doesn't have to be symplectic. It just has to extend. Okay, so that's a technical definition, but it seems to be a very nice definition. In particular, it tells us that the coordinate ring is a Poisson algebra. It has some Poisson bracket. It also has some other nice consequences. So in particular, there are finely many symplectic leaves, a holomorphic symplectic. I keep adding this word, but also it tells us that these varieties have Gorenstein singularities, rational singularities. These are results of Coulomb, Boville, Namikawa. There's a very extensive literature on symplectic singularities, so this is just a very quick overview, but just to remind what these really are. And just as an example, you know, what does the sort of labeling of symplectic leaves look like? Something like the nilpotent cone being divided into nilpotent orbits. So here's an example for type A, you know, for SLN, you have Jordan types labeled by partitions of n. Okay, and of course, we don't need to know anything about symplectic singularities to say that, but this is just a motivating example. Okay, so next, I'd like then to talk about Coulomb branches, which is maybe the little more esoteric sounding thing in this talk, but these are sort of defined quite generally due to recent results of Braverman, Finkelberg, and Nakajima, but I'll be focusing just on the ones associated to quiver gauge theories. And so rather than giving the whole general story, I'm just going to focus on the quivers because it's a little simpler, or rather you can write a definition which, you know, is more direct, let's say. So I'll give the definition and then I'll give some examples. And I hope the examples will sort of illustrate why these are interesting. Some of them will be familiar again, such as the nilpotent cone. So what is a quiver gauge theory? Well, we associate this to some quiver, Q, plus the data of two dimension vectors. I've called them V and W. So in other words, for every node of your quiver, you give two non-negative integers. And just some example, it's convenient to encode this with some notation. So if we took the type A4 quiver here, so this is just the Dinkin diagram of SL5. I've chosen some orientation. It doesn't really matter the orientation actually, but you have to choose one. And I'm going to choose two dimension vectors. So 3, 1, 2, 9 and 4, 0, 1, 2. So again, two integers for each node. And you can encode this with a nice picture like this. I'm using some sort of physics notation. So these 3, 1, 2, 9, that's become these circled nodes at the bottom. And the W, this 4, 0, 1, 2, it's become the boxed nodes at the top. So we've taken the, excuse me, we've taken this Dinkin diagram, we oriented it, and then we kind of added this framing vertices, which may be familiar from the theory of Nakajima quiver varieties. It's basically exactly the same data, and that's no coincidence. So it's just a convenient labeling. I've chosen, again, these orientations actually don't really matter. In fact, you can flip any of them, but I'm just going to choose them like this. So pick your favorite Dinkin diagram, for example, choose an orientation, choose dimensions, and choose framing also. So to such data, physicists have a way of associating some sort of quantum field theory. And it has the property that its Higgs branch is the Nakajima quiver variety associated to the same data. So as I said, this is basically the data you would choose to define a Nakajima quiver variety. That is no coincidence. It's because that would be this Higgs branch here. So the Higgs branch we already know. That's a very well-studied object, this quiver varieties. Lots of links to all sorts of areas, representation theory, enumerative geometry, integrable systems, Poisson geometry, etc. So I'd like to talk about the Coulomb branch, which is sort of the dual side of this picture, less well understood. So how do we do this? Well, this is using a definition of Braverman, Finkelberg, and Nakajima. And I'd like to just quickly overview it. The definition is going to be a some affine scheme. And so to do that, though, there's a little technical definition, and I'll go over it quickly. It's not so important for this talk, just to say that it's written as some, here's the definition anyway. So first, let's start with the formal disk, B, another spectrum of the power series ring. Then we define a moduli space, which I'll call R, and this depends on V and W. I just dropped it from the notation. It depends on our data. And it consists of the following. So vector bundles on the formal disk, I call them EI, and the ranks are encoded by the dimension vectors V. So that's for every node. And also for every one of these, there's a trivialization, but it's on the formal punctured disk. So this data together defines some point in the affine Grassmannian of a product of GL V's. But that doesn't really matter. And the third part of the data is for every node and for every edge, there's some morphisms of coherent sheaves, or which go like this. So there's some SIs and there's some SIJs. So for every node of the Dickin diagram, you have a morphism from this particular free vector bundle, this trivial vector bundle of rank WI. I guess I called it WI, but it just means a trivial vector bundle of rank WI, and it's mapping to our data, this vector bundle EI. And then for every edge in the Dickin diagram, or the quiver, excuse me, you have a map of vector bundles. So in other words, these are just to go back to our picture. So for every node at the bottom, we have some vector bundle, and the rank of that vector bundle is exactly the number that's here. And for every arrow, we have a morphism of coherent sheaves. Then for every box node, we actually have another vector bundle, but it's trivial, but the rank is still encoded by the number. And we have a map corresponding to arrows. So the boxes are trivial vector bundles. The circles are possibly not trivial vector bundles. Of course, they'll be trivializable, but that's okay. And every arrow encodes a morphism. So that's basically all this is saying. But there's one extra condition, which is these have to remain regular under the trivialization. So some technical piece of data. So we have bundles, we have trivializations, we have maps. You can try to see what happens to the maps under the trivializations. Because that was defined on the puncture disk, it doesn't necessarily extend. And so this is some extra bit. So anyway, some moduli space. It has a particular action of a group which changes the trivialization. Again, this is all sort of not so important for the talk, but just to say what the definition looks like. And then finally, BFN defined the Coulomb branch as this affine scheme over the complex numbers. It's defined as, so on this right side, you take the moduli space we just considered, you consider this group which was acting, and you take the equivariant Borel-Moore homology. And they show that that carries a convolution product, which makes it a commutative algebra. So we can take its spectrum. And that's their definition. So it's quite involved, but it actually recovers some very nice examples, as we'll see in a second. And they show that this has very nice properties. It's an irreducible normal affine variety. So in particular, it's actually finite type. The dimension is 2 times the sum of the circled nodes. It's actually defined over the integers because we could have taken Borel and Moore homology with integer coefficients instead of complex number coefficients. And they also show that it has a Poisson structure, which is generically symplectic, or holomorphic symplectic, I guess. So for all that complicated definition, you end up with some finite dimensional, irreducible affine variety. And it's Poisson, and it's generically symplectic, and it's normal. So this has the looks of something which would fit into this symplectic singularities business, but that's the part that we want to talk about today. Is this was not known yet. So, okay, so just some quick examples to show that this isn't actually as scary as it might sound. So first, what happens if you take the simplest quiver, which is just one node, right? Here's the Dinkin diagram of SL2 here at the bottom, and I've added a framing box at the top. So there's two numbers here, N and M. Those are my dimensions. I guess it should have been W and V, but I've chosen these because historical reasons, I guess, recent historical reasons. So Joel Kamnitzer has written down a nice description of this variety. In that case, it's the following. It's just it's a variety of matrices which have polynomial entries. So A, B, C, D, and just some conditions on these polynomials. So the degree, one of the first, sorry, A, the top left term is monic of degree M. The off-diagonal terms have degrees strictly less than M. And then finally, the determinant is Z to the N. So these are all just conditions on some polynomials. You can work out that this is actually just a complete intersection. It's a finite dimensional variety. So it's relatively nice. Maybe it seems sort of surprising coming from this bizarre definition, but this actually is what it is. That's one example. A little bit more generally, I'll just discuss what is known, which examples are actually known of these things, and for quivers, that is. And this is the first case. This is a theorem of Braverman, Finkelberg, and Nakajima. They said that if you're an ADE type, then you can form, so there's some associated algebraic group. Technically, it needs to be adjoint type, but let's ignore that. Then this Coulomb branch is what's called an affine Grassmannian slice, or better, actually, a generalized affine Grassmannian slice. And this data notation on the right is meant to encode a little bit of data. So this lambda and mu are somehow the same as V and W, but up to some sort of rewriting. So doesn't matter so much, but if you know the affine Grassmannian, it's just some sort of slice between Schubert varieties, roughly speaking. So this is what happens if you put in ADE data. So this is a very nice variety and important in representation theory, especially geometric representation theory. And the second theorem I just want to mention is another case that's known as what happens in affine type A. This is work of Nakajima and Takayama. They prove that you get what's called a Cherkis O variety. Not quite as well studied at the moment in mathematics, I would say, but sort of similar to a quiver variety, but with a little bit more data. So, but some other finite dimensional variety one could write down. So here's some explicit descriptions of what you get in certain cases. Okay, but maybe a little bit more concretely, since even those definitions might seem a little strange. So let's just talk about type A. And there's this data mu here. So the technical condition here will be that mu must be dominant. This is some condition on the dimension vectors V and W. Then this Coulomb branch is the intersection of a nilpotent orbit closure with a Slotowee slice. Lambda and mu can be interpreted as partitions of some number. And so you can get something like this. So much more concrete. And this is all happening within GLN for some n. And even more concrete, here's the nicest example. If you put this data, so it's the Dinkin diagram of SLN, so it has n-1 nodes. And the only place where there's any framing is at the far right. Well, I guess I flipped the arrow here. Again, this somehow doesn't matter. So the arrows are irrelevant. The dimensions are 1, 2, 3, dot, 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 to n-1. Then what you actually get is the nilpotent cone of SLN. So very nice variety. And in general, if you want to write down some particular nilpotent orbit closure intersect with a Slotowee slice, you can kind of go back and forth between the partition data versus the framing data and so on. Just a comment that these varieties are quite well understood. So in finite type or affine type, we know, for example, the symplectic leaves. We know some things about when they have symplectic resolutions. I just mentioned some work here of Dinakar Mathayo myself about the symplectic leaves in ADE type. Also previous work of Kamnitzer, Webster, myself, and Oded Jacobi. And in affine type A, again, Nakajima, Takayama. So, okay. So the upshot of all this is what happens if you take a general quiver? And this is really where, for me, the motivation lies in this whole discussion is quivers which don't have loops and with no multiple edges. You can think of those as Kac-Moody diagrams, simply laced Kac-Moody. And so what we can do is define, take this Coulomb branch definition that Braverman, Finkelberg, Nakajima wrote down. It always makes sense. It doesn't require any conditions on the quiver. And so you can just define that to be a generalized affine Grassmannian slice. And this would be for a Kac-Moody group. And the upshot of that is that there isn't really any affine Grassmannian for some random Kac-Moody group. There is for finite type, and there's some work on this for affine type by Braverman and Finkelberg. It's like sort of double loop spaces or some varieties of bundles. But the point is that basically there's no definition, but we can use this Coulomb branch as a definition. And that's why these varieties should be interesting to study. And it's worth just, I'll point out another sort of buzzword, but Braverman, Finkelberg, and Nakajima conjecture that there's some version of the geometric Satake correspondence which holds for these varieties. So not only is it like a, this is to say that this really is a good replacement or good definition of affine Grassmannian in some sense of the word. So this is the reason for the interest in these. Okay, so there's a lightning overview of these two theories. Probably too much information, but I apologize for that if that's the case. So finally, in the final part of the talk, the last few minutes, I'd just like to talk about some results of mine, which are, the main one is this, which is, so again, going back to that previous slide, I said, I want to think about simply laced Kac-Moody types. And so I'm picturing in my head that these are some sort of affine Grassmannian slices for a Kac-Moody group, non-existent affine Grassmannian slices. And the theorem is that if you take any quiver whatsoever, but with no loops, no multiple edges, and any dimensions, then this Coulomb branch always has symplectic singularities. That's the theorem. So something I sort of glossed over, but did mention was that Braverman, Finkelberg, Nakajima defined more general Coulomb branches, not just associated to quivers. I've only been talking about quivers, but there are more. And they sort of conjectured, maybe optimistically, it's not clear, that these always have symplectic singularities. So this theorem gives confirmation of this for quivers. That's the idea. This result is also already known in dominant finite ADE types by our work before, Kamnitzer, Webster, myself, and Jacobi, and in affine type A by, again, Nakajima, Takayama. And just since I mentioned these facts before, one corollary of this result is that these varieties always have finitely many symplectic leaves, and they always have rational Gorenstein singularities. So from the definition, that's not really clear at all. But by using some tricks, you can see it now. So in the last few minutes, I'll just sort of sketch where this comes from and try to relate it to some known structures. So sort of the first, oh, I guess I changed my slide and I didn't change my title. So sorry. I'm just going to talk about the ingredients. So the first ingredient is that Coulomb branches always admit partial resolutions. And so there's some data here, kappa, that I've introduced. And there's always some proper birational Poisson maps. It may not be a resolution, but it's some sort of partial resolution. This data is something associated with what's called a flavor symmetry group. This is the terminology that, from physics. But this map is defined by Braverman, Finkelberg, Nakajima in their work. And just to give a particular example would be the Springer resolution. The Springer resolution is a case of this. So this is what you could have in mind. And the second ingredient is there's always a completely integrable system which maps to the Lie algebra, the Cartan mod, the Weil group, which is just some affine space. It is faithfully flat, and it just comes from a map in equivariant Borel-Moore homology, which there's a map from the equivariant homology of a point to this ring. So algebraically, that's where it comes from, but this is actually an integrable system in the sense that these are Poisson commuting elements and maximally so. But again, what's a special case? This is what people call the Gelfand-Setland integrable system. So if you took the nilpotent cone of SLN, it has an integrable system which remembers I wrote it with some notation, but you take all of the leading minors of your matrix and you look at all of their characteristic polynomials, and you just remember the coefficients. That's the Gelfand-Setland integrable system. So this is a particular case. And so that's the two pieces of information we need to work this proof. Well, basically, the idea is that we should look at this diagram. So here we have the Coulomb branch in the middle. We have its integrable system at the top right. So that's something like nilpotent cone going to this Gelfand-Setland thing. Then we have its partial resolution on the left. Again, something like the Springer resolution here. And what we want to do is build two open subsets, U and V, so that the diagram is Cartesian. So this is the fiber product. The codimension of V is 4. And, oh, sorry, the codimension of the complement of V. Sorry, that's a typo. Complement of V. And that this thing up here is smooth and symplectic. And the reason is that this would imply that the singular locus of this resolution is sort of, the singular locus has a very high codimension. And based on some results of Beauville and Bellamy and Schedler, this would imply that you have symplectic singularities. So this is some criterion for having symplectic singularities. Sorry, I'm rushing a little bit, but basically one more slide. So how does this work? This is a statement of theorem. Well, the idea is that if you take this quiver theory and you take the integrable system, you can actually understand the fibers pretty well. This is based on some work of Braverman, Finkelberg, Nakajima, but analyzed a little bit more explicitly in the quiver case. So étal locally, the fibers always look like products of other quivers. So you get some smaller quiver gauge theories. And the theorem is just that you can choose an open set. So just coming back here, this open set, you can choose it in such a way that you can control the quivers that come up pretty well. And you can show that everything you get is smooth and symplectic. So this gives the diagram on the previous page, and that's how the theorem gets proven. So that's the proof without details at all. Okay, and if it's okay, I'll just list some questions. So one is, this doesn't give any enumeration of symplectic leaves. It's not explicit. It's just, there's finitely many, for example. But it would be nice to know what they are. It should have some interesting representation theoretic meaning, but it was like partitions of n or something before. What does it mean in general? I don't know. That's one question. Another minimal model type program question, is it a Q factorial terminalization? When is it a resolution? So we had the Springer resolution. Does that always happen? I don't know. Typically, the answer is going to be no, even for a sort of generic one. Another question is, I omitted loops and I omitted multiple edges, but what happens then? And what happens in symmetrizable types? But it's sort of a whole other story. And finally, what happens for other Coulomb branches? So there's this conjecture of BFN that they always have symplectic singularities. Here we've seen that the quiver ones do, but it's still not known in general. And so that's sort of an open question. So sorry for going a little over. I'll leave it there. Thank you for listening.